Today we'll be talking about power sets. From their name, you might think these sets have some sort of extra energy or something, but it's not really that at all. It's more like what happens when we exponentiate a set and we put the set as the power in the exponent. Anyway, let's get to it. The power set of A is the set of all subsets of A. More specifically, B is in the power set of A if and only if B is a subset of A. Let A be the set with three elements, a triangle, a square, and a star. Notice that A has size 3. Okay, what does the power set of A look like? Let us list all the subsets of A. First, there's the empty set. Then we have three subsets with one element each. Then we have three subsets with two elements each. And finally, A is a subset of itself. Notice that the power set of A has cardinality 8, which is 2 to the power 3. We point out that some of the concepts and some of the notation here can be confusing. Let us again take A to be the set with triangle, square, and star. We list 8 statements below, each of them using legal mathematical symbols. But which of these actually makes sense? In fact, only 3 of these statements make any sense at all. The triangle is an element of A, and since the single element is not a subset of A, it has nothing to do with the power set at all. The singleton subset, which is the set consisting of one element, in this case the triangle, is a subset of A, but not an element of A, and it's also an element of the power set, but not a subset of the power set. We have a theorem. If A is a subset of B, then the power set of A is a subset of the power set of B. To prove this, assume that A is a subset of B. Let C be an element of the power set of A. This means that C is a subset of A, but A is a subset of B, so C is a subset of B, and therefore C is an element of the power set of B. Here's another theorem. If the finite set A has size n, then the power set of A has size 2 to the n. Note, sometimes people denote the power set of A by 2 to the A, and that's a notation that's motivated by this theorem. This notation is nice because it really is thinking of exponentiation of a set and not a number. This is an important theorem, and we will actually prove it 3 ways. The first proof is a purely combinatorial one. Let us write out the elements of A as A1, A2, etc. up to AN. Now let us construct an arbitrary subset of A. How many ways can we choose this? We get to choose if A1 is in B or not in B. That's 2 choices. We get to choose if A2 is in B or not in B. This is 2 choices, etc., etc., etc. And finally, we can choose if AN is in B or not in B. This is 2 choices. We had n independent decisions, and at each step we could have picked one of 2, so the total number of choices is 2 times 2 times 2 n times, which is 2 to the n. Okay, the second proof, which is computational. For any subset B of A, let us encode B by a binary sequence, B1, B2, B3, all the way up to Bn. And we say that Bi is 1 if Ai is in B, and Bi is 0 if Ai is not in B. Clearly, knowing the sequence tells us exactly which elements are in B, and vice versa. Given any subset of B, we can write down a binary sequence of length n. For example, the empty set corresponds to the string of all zeros. The set consisting of, say, A2 and A5 is a string that starts 0, 1, 0, 0, 1, and then ends with zeros. The set A itself gives the string of all ones. We can count how many such sequences there are. In fact, they encode the integers 0 to 2 to the n minus 1, which is a total of 2 to the n integers. The third proof uses induction. First, let us do the base case. Let A be the set consisting of a single element x. Then A has 2 subsets, the empty set and A itself. Since 2 to the 1 equals 2, this checks. Now, we are going to assume that the theorem holds for a given k. Specifically, any set A of size k has a power set of size 2 to the k. Okay, so let B be a set of size k plus 1. Specifically, B has the elements B1, B2, all the way up to bk plus 1. And let A be B with the last element thrown out. So notice that A is 1 smaller than B, so the size of A is k. By the induction hypothesis, the power set of A is size 2 to the k. But also notice that any subset of A gives rise to 2 subsets of B. If we take a set C, which is a subset of A, then C is also a subset of D. And if we take C and throw in bk plus 1, we also get a subset of D. Both of these 2 subsets are subsets of B. Therefore, to any C, which is a subset of A, we get 2 subsets of B. Therefore, the power set of B is twice the size of the power set of A. By the induction hypothesis, that's 2 times 2 to the k, which is 2 to the k plus 1, and we are done. Let us now define n choose k to be the number of ways to choose a subset of size k from a set of size n. We sometimes denote this number like a 2x1 matrix. Now here's a fun fact. N choose k actually has a formula, and it is n factorial divided by k factorial divided by n minus k factorial. We aren't going to prove this now, since we don't need it for what we're about to say, but this is a very important quantity, and we'll deal more with it in the future. But let us first note the very interesting corollary of our last theorem. The sum over k from 0 to n of n choose k is exactly 2 to the n. How do we see this? Let A be a subset of size n. We know that the number of subsets of A is 2 to the n by the previous theorem, but this is the sum over k of the number of subsets of size k, which by definition is the sum over k of n choose k. And that's it. Anyway, this will be a good place to stop.